So here I want to use a substitution, the u is tangent of x, to show that this integral is equal to 1 over n plus 1. Okay, so we're going to use u substitution. We'll let u equal tangent of x. That means du is secant squared x dx. And now I'm just going to replace everything. So I have tangent of x raised to the n plus 2 power. So I'm going to replace tangent with u, and I'm going to have that to the n plus 2 power, plus tangent to the n, I can just write that as u to the n. Now dx is a little tricky. So far I have du is equal to secant squared dx. Okay, so if I were to solve for dx, that would be cosine squared du, because I would have du over secant squared, and 1 over secant squared is just cosine squared. Okay, but now that's not in terms of u. So how do we get in terms of u? Well, let's look at a right triangle. So the angle is x. We said let u equal tangent of x. Okay, so think of this as u over 1. Tangent is opposite over adjacent. So doing Pythagorean theorem, the hypotenuse is u squared plus 1, square root of that. So cosine squared is adjacent over hypotenuse. So that would just be 1 over square root of u squared plus 1 squared du. So it's du over u squared plus 1. So this is dx. So we'll just put it over here. And now we can also change the limits if you want, or we can do it after, but we'll just get it out of the way. We know these limits are in terms of x because it's dx. So plug it into this equation. If x equals 0, u is tangent of 0, which is 0. And if x is pi over 4, tangent of pi over 4 is 1. So this simplifies really nicely. At this step, we notice that we have u to the n plus 2 power and n power. So I can factor out a u to the n, and I'll be left with u squared plus 1. And then it's du over u squared plus 1, integrating between 0 to 1. The nice thing is the u squareds plus 1 will cancel, and so we'll have the integral from 0 to 1 of u to the n du. So we'll do the power rule. Antiderivative is u to the n plus 1 over n plus 1. We'll evaluate it from 0 to 1, and so we get 1 over n plus 1. Okay, so this part is complete. Okay, let's move on to the second part. So now it says, hence, find the exact value of this integral. But you may be asking, well, they told us in terms of tangent, right? So if I were to rewrite what they had in the first part, so if the integral from 0 to pi over 4, tangent to the n plus 2 of x plus tangent of x to the n dx, we said was 1 over n plus 1. But here we only have in terms of secant. So what's the connection between the tangent and the secant? Well, we know that 1 plus tangent squared is secant squared. So I can replace secant squared with 1 plus tangent squared. Well, that's okay, but what about secant to the fourth? Well, I have to square both sides of the equation to get secant to the fourth. Okay. So I have 1 plus tangent to the fourth, x plus 2 times tangent squared. Okay, so this is equal to secant to the fourth. And now we can just substitute it in. So we have the integral from 0 to pi over 4. Secant to the fourth is 1 plus tangent to the fourth plus 2 tangent squared. and then minus secant squared, we said is 1 plus tangent squared. And here it's very important to put parentheses around the 1 plus tangent squared, because you want to subtract that whole quantity. So at this point, the 1's are going to cancel. We have 2 tangent squared minus tangent squared. That's just going to leave us with 1 tangent squared. Okay. So to rewrite this, we have the integral from 0 to pi over 4, tangent to the 4th x plus tangent squared dx. Well, this is nice because the exponents are 2 apart from each other, right? So if you look back here, n plus 2 and n, we have to the 4th and squared, so that's only 2 away. So clearly, based off this formula over here, n has to be 2. Okay, so n here is 2. Our answer was 1 over n plus 1, so if we substitute n equals 2, we get 1 over 2 plus 1, which is a third. Okay. And that's our answer for this part. Look at this problem. So the nice thing is that the exponents are 2 away from each other. Okay? Because recall, if we go from 0 to pi over 4, tangent of x to the n plus 2 minus tangent of x to the n, this was equal to 1 over n plus 1. Now the problem is, though, we have these coefficients of 5. So it doesn't work out as nicely as we want. So in order to go around that, I'm first going to include only the ones with the coefficient of 1. So let's ignore the 5s for just a second. So at this point, we can easily use the formula and be done with it. But we will be missing 4 tangent to the 7th plus 4 tangent to the 5th. So we're just going to add them to the end. All right, so now these two integrals are equivalent. Okay. So the key to doing this is to group them. Okay. So you can actually break it up into 3 different integrals, but that's a lot of work. I don't think that's necessary. So pretend these are 3 different integrals. So for the first quote-unquote integral, it's tangent to the 9th plus tangent to the 7th. Clearly, n here is 7. Okay, and then tangent to the 5th plus tangent cubed, n is 3. And for the last one, n is 5. So for the first integral, the coefficients are 1, so we use the formula 1 over n plus 1, which is 1/8. The second integral, coefficients are 1, so we use 1 over n plus 1, which is 1/4. For the last integral, they both have a coefficient of 4. So I can pull that out. And then it just becomes tangent to the 7th plus tangent to the 5th, which we know is equal to 1 over n plus 1, where n is 5. Okay, so now it's just simplifying. 1/8 plus 1/4, let's see, that's 3/8, plus 4 times 1/6, that's 2/3. So if we add these up, that's 25 over 24. Okay. And that's our final answer.